Welcome to Fundamentals of Telecom 2. In this video course, we're going to drill into the technology of the PSTN just a little bit to understand digital transmission. We'll start off looking at how voice is digitized, the standard way of doing that on the PSTN called a DS0, how those are combined into higher speed streams, DS1s and DS3s. We'll take a look at the applications for digital besides voice. We can talk about data, of course, and we're going to talk about digital video a little bit. And then in the second part, we're going to take a look at digital transmission on the PSTN and understand the idea of channelized multiplexing. We'll take a survey of different technologies like T1, T3, SONET, and dense wave division multiplexing. Now, before anybody says this is all old stuff and we don't need to know it, the vast majority of the installed base runs on SONET fiber optic transmission systems and channels. Yes, we will be going to an all-IP packetized network sometime around 2025. The changeover should be complete. But a lot of the time these days, we're talking still about circuit-switched DS0 communications for voice, and we're talking about channelized SONET fiber optic transmission systems. So this is still part of the fundamental knowledge you have to understand the telephone system. To make that a little bit more clear, let's go through an example of converting from analog to digital and back again. And we're going to use voice as an example, and there's a real good reason for doing this because the bulk of the public switch telephone network is all designed to carry digitized voice around. Just to put this into context, where this is going is on the line card on the telephone switch. We use analog techniques on the last mile and a half of wires, but the first thing that happens to the information when it gets the line card on the switch is it's digitized. And it moves through the switch as a sequence of ones and zeros. All of the transmission is digital, so it goes to the far end switch as a sequence of ones and zeros, moves through the far end switch as ones and zeros. But if you call me, I don't have a digital access line. I don't have ISDN. I've got POTS, plain ordinary telephone service. I've got an analog access line. So on my line card, that sequence of ones and zeros has to be used to recreate the analog waveform to deliver it the last 2 miles down the wires to my home. So we do analog digital at the near end line card and then digital analog at the far end line card. To do the analog digital conversion, there are 3 steps: quantization, sampling, and coding. What is quantization? Well, look at this wave here. This could be, for example, the voltage on the wires while you're talking on the phone. And you can see that it's continuous in value. It can take on any fractional value it likes, and it's continuous in time. There's always a value on the wires. We're not turning it on and off. The first step is changing this from being continuous in value to being discrete in value. And what we do is we take the range of values that the signal could possibly take on and divide it up into a number of steps or levels or bins, they're called sometimes. And then if we want to know what the value of the signal is at a particular instant in time, well, we don't look and say, well, it looks like at that time it has minus 0.73 volts. No. It's in bin number 3. It's level 3. Nice whole even numbers. No more fractions. This is called quantization. What's another example of quantization? Sugar cubes. If you have a bowl full of loose sugar, you could take any fractional value of a teaspoon you wanted. And it would be very difficult to tell somebody else how much sugar you have because that's just some random fraction. However, if we take that same sugar and quantize it into sugar cubes, your choices are now 0, 1, or 2 lumps. And it's very easy to tell somebody else how much sugar you've got because you just have to tell them what increment number you're at. The second step on this chart is sampling. Quantization changes the signal from being continuous in value to being discrete in value. Sampling is the same thing but in time. And the way that this works is like a clock on a regular timed basis. We look at the signal and take a sample of its value. So at the first sampling time, we look and we see that the signal is sitting right here, which is within level 5, so we write down a 5. And then a little while later, it's within level 2, so we write down a 2. Then a 1, then a 4, then another 4, then a 2, then a 4, a 5, a 2, a 3, a 6, a 3, and a 1. And we end up with this sequence of numbers representing where the signal was at each of these times. This is our digital signal. And you can see that it's discrete in value and in time. Sorry to break the bad news to you, but you know all of these circuits that everybody calls digital circuits? They're not. Never heard of a 5 before. If you sent them a 4, they would have no idea to what you were referring. They've only ever heard of 1s and 0s. They're all binary transmission systems. So the last step is the coding step. We have to somehow take the raw output of this quantization and sampling and code the values of the samples into 1s and 0s. Anybody who knows binary math would know that you could represent a 5 as a 101 and a 2 as a 010 and a 1 as 001. That's the easiest way to do it. That's straight decimal to binary conversion. There are lots of other ways of doing that coding step. But in any case, what we end up with is this stream of 1s and 0s. This is what gets transmitted through the telephone switch. This is what gets transmitted over the fiber to Hong Kong. And this what gets transmitted through the telephone switch at the far end. Now, as I said, if you call me, I don't have a digital access line. I've got an analog one. So we have to do a conversion back to an analog representation. So let's take a look at that.